Hello everyone. Today we are going to learn how to use a software for wastewater treatment process design. And as I mentioned last week, we are going to study how to use the Steady, which is the simplest softwares available for educational purpose. So what we are going to do is how to learn Steady and what's the specific functions and how can we interpret the result that is generated by this software. Steady is a free software um, which is available through this website, and this is a very simple software, and this is developed by this University of Texas. So you can download this from here, and this is just one of the screenshots for these study softwares, and this screenshot actually shows almost all functions that is included in this software. So today I'll tell you how you can use this one, and probably in the next lecture, you'll have a chance to actually operate with these softwares. First of all, we have to look at some of the background um, of this software. Steady is a steady-state wastewater treatment plant modeling program which was developed by Louis Garnicia and Spatel, and it was actually developed in 1999. So this is more like a very classic software. And when you first learn, you will see this kind of this screen which tells where this is developed and what's actually the license for this software. But one thing that I have to mention here is, as you can imagine from the name of this software, this is purely for steady state modeling. So steady state means that everything is constant through time. So in fact, in reality, every process is time dependent. However, in steady, we only can see the systems that where everything is not changed with time. So that's one thing very important, because most commercially available softwares can actually simulate not only the steady state behaviors but also the dynamic behaviors. So that's actually the big difference between the free software and commercial softwares. So Steady is a computer program that provides a generalized model to represent wastewater treatment plant. So it only has very simple models. In fact, there are a lot of factors that we have to consider when we have to design this wastewater treatment plant, and Steady include only a small portion of that kind of functions, but it's still enough for beginners, because that's actually the starting point that we can actually understand what kind of things that we have to do when we design this wastewater treatment process. This model assumes steady-state conditions for the influent to a given plant and characterized wastewater with the traditional environmental engineering parameters, including BOD, TSS, VSS, TKN, and NH3N. As I mentioned, that this is just the program for steady-state modeling and steady-state process simulation. And once a valid plant layout has been created, we can actually use steady to predict how much BOD can be removed and how much TSS can be removed, something like that. So this is very useful because, as I mentioned, that the biological process include some kinetic parameters and kinetic equations, and some biochemical reactions are involved. So it's a little bit complicated if you wanted to solve everything by hands or using a calculator. So under that kind of circumstance, Steady is a very convenient tool to help you. So what can Steady do? Steady can calculate the plant-wide mass balance and the general dimensions of the unit process involved. So it can actually solve the mass balance for biomass, mass balance for total suspended solid, and BOD, and sometimes nitrogen balance can be solved using this Steady. And another function, although this is a very simple function, but it can also allow the determination of the dimensions of the unit process, which I will actually show you later. So these are two main functions that this Steady has. Also, once the mass balance has been calculated, Steady can display the calculations performed for each unit process. So you can actually see how much BOD can be obtained after passing through this bioreactor, after passing through this primary treatment, after passing through this sludge treatment. So for in each important point, you can actually get some information on water quality, water quantity, something like that. So this is again very convenient function. So this is one of the examples of how this mass balance can be solved. So in this case, you have some of the streams, and that means the stream between primary and secondary treatment, and discharge point, influent, and primary treatment. In each stream, you can actually solve the mass balance to get information on flow, BOD. TBOD means the total BOD. SBOD, soluble BOD, total suspended solid, VSS, which is microorganism or biomass, total killed nitrogen, and ammonia nitrogen. So they are so you can actually see how they changes within the system. Steady provides a graphical user interface where the user can create a plant layout just by drawing a flow diagram. So this interface is very convenient because some softwares you have to manually put every parameters without having any graphics. So it's not really intuitive, but Steady is very intuitive software so that you can actually draw the process and set up the parameters, get the result. So that's very good. The interface provides a dialog boxes to edit parameters of each unit and a menu and toolbar to access the program's comments. So you don't need to type everything to determine or design the systems. You only need to use the graphical user interface, and then your input can be minimal. So in this version of Steady, I don't know in the future where this new version will be available or not, but we are currently stick to the very first version of this Steady. So you just learn what kind of things can be done by this Steady. So in this study, the following unit processes have been included. The influent and effluent, they are like starting point and the end point. Primary settling tank means primary treatment or primary clarifier. And for secondary treatment, in fact, the essence of this study software is to design and simulate secondary treatment. So for this secondary treatment or the activate sludge process, study has three different models. So later I'll explain the details about the mathematical model for steady activate sludge systems. At this point, you just need to learn what's the first model, what's the second model, and what's the third model, and what's the limitations for the first or second or third model. So that's all you need to learn. You need to know before you actually try to use this study software. Anyway, we have three different mathematical models depending on the situation. So you need to choose one of them. And depending on your selection, the result may be different. So you needed to actually know which model is appropriate for a certain cases and which model is not really appropriate for the another cases. And in addition to primary treatment and secondary treatment, there are some unit processes including the dissolved air flotation, sludgy gravity thickening, sludgy digestion, sludgy dewatering. So these are just for the sludgy treatment. And stream splitting and stream mixing are also included because sometimes you need to mix the stream, sometimes you need to split the stream, otherwise the process cannot be really realistic. So these functions are also included in this study software. So these are all the things that you needed to learn before you actually try to use steady. Also, you needed to learn the limitation of this steady software. So what steady cannot do is one of them is the unsteady state simulation, as you can just imagine from the name of these softwares. This is not for unsteady state process design or simulation. If it is, you have to change the name from steady to unsteady, but it's not, so that means it's just for steady state simulation. And steady is just for conventional biological treatment, so it cannot calculate any advanced treatment such as the phosphorus removal or denitrification. In fact, what we have as the unit processes are the just primary treatment and activate sludge process, not the anoxic or anaerobic bioreactors. So we cannot expect any phosphorus removal or the denitrification under this circumstance. So that's why study cannot predict any phosphorus removal efficiency. Economic analysis, although it's very important in every engineering design, but this study is just a simple software which cannot actually do this economic analysis. So if you wanted to do some economic analysis, you have to use other tools. So if we have enough time in this semester, I'll just tell you how we can actually calculate the construction cost and operational cost for a certain wastewater treatment process. In fact, there is a user manual which is really helpful when you wanted to learn the basic functions of STEADY, although the manual is just a manual, so you cannot learn everything from the manual. But sometimes, if you are curious about a specific function of this software, you needed to look up this manual. So that's also included in this program package. Okay, let's start to learn how to use STEADY. So we'll start from a very quick tutorial, which is actually an example of the use of STEADY. So when we first started this program, you will see the introduction screen, which I already showed you, and then you will just see a blank screen. So you needed to add something before you actually design something. So the blank screen means that you have to choose the basic design schematics. So in order to do that, one thing that you have to understand is this wastewater treatment process consists of a few unit process. So starting from this source and destination, you will have a series of unit processes. So you can actually select the unit process by clicking this icon, so this one. So by doing this, you can choose one of these unit process, and you can just select that to put it on the blank screen. So in this screenshot, we see that we choose that this source to start with this design, and so after doing that, you'll see this kind of screen. And you can choose any location from this on this screen and on this canvas. However, it's always very good to see or very good to start from the left side. So you can just see that this water flows from the left side to right side. So you'll eventually have the end point on the right side. But that's all your call, because if you wanted to do that, you can just choose the opposite directions. That's all what you needed to do. Okay, each unit process that you can choose from this STEADY program requires some input. So by clicking this icon, you can actually see this dialog box to edit the parameters. So what you have right now is the source. Source means the wastewater source. So the wastewater should have two information, the quantity and quality. So the parameters that you have to change to start with is the flow rate and wastewater composition. The flow rate, we have two units, liter per sec and megagallon per day, and we learn how to change the units. And in fact, this software can actually change from one unit to the other unit. Wastewater compositions, you have actually three parameters to edit. So that's the VOD5 is the TVOD5 is total biological oxygen demands after 5 days of the measurement. TSS is total suspended solid and TKN is total killed nitrogen. So this means the total quantity. And among these all BOD, some of them are soluble and some of them are insoluble or particulate. So that information is also required to estimate the removal efficiency by primary treatment and secondary treatment. So that's the portion of the soluble VOD among total VOD. This is the portion of the volatile suspended solid among the total suspended solid, and this is actual concentration of ammonia nitrogen. In fact, we are talking about this activate slurge process or the oxic reactor. So we can actually see some of the conversion from ammonia to nitrate or nitrite. So that kind of reaction can happen, but the further reaction, such as the denitrification, cannot happen. So we only need to have this TKN and ammonia nitrogen to start with. So that's just one of the examples that you can start with by when you edit the input. Then you can add the other unit processes. As we just learned, the simple wastewater treatment process include primary treatment and secondary treatment, and they are all available from the icon. So by clicking that and by selecting this unit process, you can actually choose that, and you can choose them, and you can actually place them to the positions, and you can later you will connect these between these unit processes. Anyway, in this screen, we choose the primary settling and activate slurge process with the model 1. As I mentioned that there are 3 models that we can choose from study library, and here the simplest model was chosen, and the endpoint is the effluent. So this is actually the wastewater treatment plant. So the influent is supplied, the effluent is discharged. So what you have to do is to design the actual configuration for this wastewater treatment system. Once you choose the unit processes, you have to connect them. Otherwise, you cannot actually get any result. So you can actually have the lines by clicking that by using these icons, and you can actually connect from source to primary settling to activate slurge to the effluent. So this is one of the simple the configuration for the wastewater treatment. In fact, in every wastewater treatment systems, not only the water but also the solid should be treated. So the water treatment as well as sludge treatment should be considered. So in this example, we consider not only this water but also this sludge treatment, so that this DAF thickening was considered because it allows the concentration of the solid materials from the sludge to reduce the water contents, so that later we can actually treat this easily. So here the solid liquid separation, dissolved air flotation is selected, and then stream mixing is also selected to mix two streams into to make a one stream. So that's what we can do at this step. Now move the unit to a location, proper location, and then you can actually place everything, and then you can see something like that. As a next step, and we have to connect this water treatment process to the sludge treatment process. So flip the mixing box. So now the inlet comes from the right and the outlet points to the left. So previously we had something like that, but we can flip that so that we can change the directions, flow directions. And we connect these two lines. So the first line comes from the sludge from the primary settling, and the second line comes from the sludge from the activate sludge process. Of course, the DAF was applied to increase the solid parts, and then you can actually get this the sludge. So after doing that, the flow diagram now looks like that. Sometimes it's enough to collect the sludge from the primary settling and secondary clarification, but sometimes we need to stabilize this sludge before we actually dispose it. So in many large-scale wastewater treatment plant, the sludge digestion is applied to reduce the amount of sludge to produce the methane gas and stabilize the sludge composition. So that's why we place that, but that's just one of the options. So it's not really inevitable. So depending on the design, you can even include other processes, or you can just take out this sludge digestion or the DAF. Anyway, the important part is the wastewater treatment through this primary settling and activate sludge process. If you wanted to delete the right mouse button and select delete stream. So if you make a mistake, you can just select that using the right mouse button and delete the stream and delete the unit process. So you can actually change everything if you want. So now we have everything connected, I guess. So if you follow this flow diagram, the wastewater comes from the source, and it is actually mixed with the wastewater coming from the sludge treatment. Then this wastewater is supplied to the primary settling. So some of the suspended materials can be removed as a form of sludge, which will be here, and the supernatant will be supplied to the activate sludge process, because the primary settling cannot remove any soluble materials. So these soluble organics, soluble nitrogens, they have to be treated by the activate sludge process, so the microorganisms can convert these to the carbon dioxide or biomass, and excess the biomass will be taken out from the system. So this will go to the sludge treatment process, And the supernatant from the secondary clarification will go to the effluent point, so this water may be discharged or recycled. And this sludge is mixed with the sludge from the primary settling. So this is the final layout for the plant, and then with that we can actually start calculating the water quality and water quantity in each point. So after doing this, one thing you have to remember is this program is not very stable. So sometimes the program crashes and there's no function like autosave, so you'll actually lose everything when the program is crashed. So this is a very good time to save the file. So by clicking the file menu and select save, and you can actually choose a name for the file and you can save the plant layout. Next, just start calculating the mass balance. Of course, if you wanted to adjust the parameters for each unit process, you can do that before you actually calculate this mass balance. But just assume that you actually adjust all process parameters or parameters for the unit processes, and just assume that we are ready to calculate. So by clicking this button, which is actually located here, we can now see the water quality. So in fact, this is kind of non-linear equation, or simultaneous series of equations. So the program actually iterate. So after doing some iterations, the final result will come out. Sometimes the iteration fails if this calculation is really complicated. However, in most cases, the iteration will be done within a second, and you will get this kind of dialog box, which contains the mass balance summary. So in this case, we have this ID, which you can identify from the process layout, and each stream has the descriptions. So for instance, the ID2 means the effluent from the aeration tank. So this stream is actually located between this the aeration tank to this secondary clarifier, something like that. So you'll have a lot of streams, and will have these water quality parameters as well as water quantity parameters. So that's the result that you want. So this is pretty much simple, as you can just imagine. And you can choose different units. So for instance, you can just have the units of liter per sec plus milligram per liter, or you can just select the units of cubic meter per day plus kilogram per day. The first unit is for the flow rate. Second unit is for the concentration. After calculating the mass balance, the label in the box titled MB current will say yes in green, which means that the mass balance displayed in the window is current, or in other words, the mass balance reflects all current parameters of the plant. If you change any of the parameters of the plant, like flow coming to the source, the label will change it to no. So when the mass balance is current, you can click the Show Calc buttons to display the calculation performed at each unit process. So that's final result, and you can actually print out the result by selecting File, Print, FD, and MD. MB, the FD is flow diagram, MB means the mass balance. So that's what actually you wanted to print out. You wanted to have the output files. Sometimes you can just capture the screen to get some information. So whatever you can actually get some information from the final calculation. Or instead of printing the calculation, we can actually export that to Microsoft Excel. Go to File menu, export tables in the and in the Save As dialog box, enter the name and directories, and then you can actually export the numbers that you get from this calculation. To increase the readability of the information in Excel, and you can actually change the column width and give the column A and C greater width, or that's all very minor, this manipulation. This is actually the so that's all. So that's what you needed to do that. So as we have just gone through, this use of the study program is very simple and very intuitive. Once you learn about this basic concept and the meaning of unit process and the parameters that you have to change when you select the specific design. Okay, that's actually the exercise, and let's go to see the details. So we'll see each part of this study software. So the first thing that we'll see is the toolbar. So this toolbar is a very simple interface to access the main functions of the study program. So the first one is new file, second one is open file, third one is save files, first is print of the FT and MB, and this is the main function. So if you wanted to add reactor or add unit process or add influent and effluent, you have to choose that. And this one, once you complete the process the design, you have to click this button to calculate mass balance. And this calculate cost, I guess the authors initially tried to include this one, but right now this button is meaningless because they didn't actually include this kind of function. So just ignore this one. And sometimes the process diagram is too big to be included in one screen. So in this case, you have to zoom out. Or if you wanted to see the details, you have to zoom in. When you choose source and when you try to edit the parameters in this source, you have to know the meaning of the parameters. So the Q is flow rate, BOD5, TBOD5 is total BOD5, SBOD5 is the soluble BOD expressed as a percent of the total BOD5, TSS is total dissolved solid, VSS is the volatile suspended solid expressed as percent of TSS, TKN is total killed nitrogen, and NH3N is ammonia as nitrogen. And in fact, this has the units of this one. So if you wanted to change the unit, you have to manually calculate the flow rate. So for instance, if you only have this flow rate in the unit of cubic meter per day, you have to convert this one to this one with this unit. In fact, each unit process has default values, so without even changing anything, you can actually just use these unit processes to get the result simply get the result. So that's just an example. So in real design, you have to change this default value. And for this activist large process, as I mentioned, that there are three models. The first model is one of the classical models, which was initially developed by this Metcalfe and Eddy. So the details of this, the activist large model 1 is described by this textbook, Wastewater Engineering, Treatment, Disposal, and Reuse. So let's skip the details and let's try to explain the parameters that you have to determine when we select this activist large reactor. In fact, this is a biological reactor, so this means that there are microorganisms, and microorganisms they have very important parameters such as yield, this FM ratio, SLT, the HLT, and the decay rate, something like that. So those parameters should be determined when you use the activist large reactor. Fortunately, we already have some default value. So these biological parameters, for these biological parameters, we can just use default values unless we have additional information. So you don't actually need to change these four parameters if you don't have any other information. But if you have more specific information on the microorganisms in your bioreactor, you have to manipulate these parameters, these three parameters. And these MCLT, V, and X, they are like these operational parameters that you have to adjust to optimize the conditions for the biological reactions. So that's actually what you have to determine. Later we'll see how we can actually determine and these parameters. And another parameters that you have to be careful is the milligram VOD per milligram VSS. That's the ratio of VOD to VSS in slurs. And there are two ways that we can actually design the process. The first way is to design based on FM ratio and MCLT, and the second way is to design based on yield and KD. So that's the actual model, the number, and the control means and when we wanted to fix the MCLT and the reactor volume to calculate the MRSS, we have to use this control number 0. And if you wanted to fix MRSS and reactor volume to calculate MCLT, the control ID is 1. And if you wanted to fix MRSS and MCLT to calculate reactor volume, we can actually use the control ID 2. And sometimes we needed to determine the recirculate rate, and so if we fix the MRSS for the recirculated stream and calculate recirculate flow rate, we have to use the recycle of 0, or we can determine the MRSS for the recirculated stream by fixing this recirculate flow rate. And this information is also important because not all MLSS contains microorganisms. So this ratio of MLVSS to MLSS is important. And so, you can also choose a default value if you don't have additional information. QL, XL, BOD, the effluent, and TSS effluent, they have to be selected. And we can also have additional information for the number of aeration tank, number of clarifications, side water depths, side water depth for the aeration tank, side water depth for the clarification tank, and length width and overflow rate. And these parameters are required to determine the dimensions and the flow rate. So they are like additional parameters to be considered when you actually design the bioreactor. So let's explain a little bit more about the process modeling in STEADY. This model takes the characteristics of the influent stream and the specified effluent total VOD5 and then calculate operational parameters such as MLSS, concentration, and slurry production. So which means we'll have the input conditions and we have the target conditions, and the process design means that this program can choose the operational parameters to satisfy these conditions. So the MLSS or sludge production can be calculated. The calculations are based on BOD5 removal, which is considered as the difference between the influent BOD5, total BOD5, and effluent soluble BOD5. The basis for this is the assumption that all BOD5 that enters the system in particulate form is hydrolyzed in the aeration tank. In fact, this is very questionable assumptions in real cases, but this can actually simplify the problems. So this is why we actually choose this assumption for the first model. The soluble VOD5 of the effluent is calculated from the specified effluent total VOD5 and the VOD contents of the effluent. The excess VOD sludge produced in the system is assumed to exit through the clarifier effluent and through the waste sludge output. The calculated mean cell residence time is based on the cell mass that leaves the system through these two outlets. The soluble VOD5 has the same concentration in all outlets and is calculated from the effluent total VOD5 and the VOD5 contents of TSS. And that's all for the organics. And then let's talk about this nitrogen. No absorption or transformation of ammonia is assumed. So the concentration of NH3N in all streams is the same as the influent. It is also assumed that this nitrogen that is not in the form of ammonia is particulate and that is conservative and leaves the system in proportional to TSS. So TKN is calculated as the sum of the corresponding ammonia, nitrogen, and the particulate nitrogen, the concentrations at each outlet. So this statement means that the first model that we are talking about here does not have any functions for calculating the oxidation of ammonia. So no transformation of ammonia is considered. So if you have the ammonia, you will have the same concentration of ammonia in the effluent. So this is just the mass balance, not this chemical reaction or chemical transformation. So that's another the limitation of this model. So in other words, if you have this ammonia in your influent, you may want to use other models than this the ASM first model. So we actually have another choice, the second model. So this looks similar from to the previous model, but this has different equations inside this the reactor. So this model, unlike the previous one and others, does account for influent suspended solid and for the non-biodegradable part of influent suspended solid and MRSS. In fact, in real cases, the influent SS cannot be completely hydrolyzed. So it's reasonable to assume that a small portion or a large portion of these influent SS and MRSS are non-biodegradable. So that's the difference between the first model and the second model. This model allows a more calculate estimation of the sludge production in the system. Although the model was developed with low waters, for instance without primary sedimentation, it has been shown to be applicable to plants that have primary treatment. In fact, the reason why this model is useful is if you don't have any primary treatment, sometimes in a small scale wastewater treatment, it's possible. So if you don't have primary treatment, the MRSS and these SS, they will contain significant amounts of non-biodegradable particles. So this is very useful under that circumstance. However, even with the primary clarification, it's still possible to have some non-biodegradable particles. So it has been shown to be applicable to plants that have primary treatment. And the third model, this model can have this nitrification model. So in the first model and the second model, they cannot consider any biodegradation of the ammonia. However, in the third model, the nitrification model is included so that the conversion of ammonia to nitrate can be considered in this by this model. So if you wanted to know how this nitrogen is converted within the system, the model 3, the third model, may be the best selection, best choice. So this reactor is the only one in study that has a model where TKN is actually consumed. For other models, TKN is not is consumed. So this is about the primary settling. So if you wanted to calculate the treatment efficiency, we have to choose the process parameters, and if you wanted to determine the dimensions, we have to choose these design parameters. So process parameters include TSS removal, TBOD removal, and sludge concentration. So this unit process simply considered the percent removal of TSS and TBOD. So once you choose this removal efficiency, we can actually calculate the concentration of the effluent fairly simply. Sludge concentration by if you have this value, you can actually see how much sludge is produced by this primary settling tank. Design parameters, on the other hand, are useful to determine the size of the reactors. So the number of units, overflow rates, width, tank geometry, and wear and width ratio, length width ratio, they are all used for determining the size of the primary classification. So this is an example of how we can use these design parameters to actually design this primary settling. But one thing you have to be very careful is for primary settling tank, we have some design criteria. So we cannot violate these design criteria, otherwise the system may not work. So when you choose these design parameters, you always have to consider these design criteria. For instance, the overflow rate should range from 30 to 50. Peak flow rate should range from 80 to 120, something like that. So these are the essential information when you wanted to make this design as realistic as possible. In terms of the process modeling, the primary settling tank does not perform any mass transformation. Instead, it solves the mass balance between the influent and the two effluent, the sludge stream and overflow. So the user specifies the percentage of TSS and TBOD5 on a mass basis captured in the reactor. Then the sludge flow rate is calculated using the specified sludge concentration, sludge solid concentration. The concentration of the overflow are calculated based on the specified removal efficiency of the influent TSS and TBOD5. The concentration of soluble contents such as soluble BOD5 and ammonia are fast unmodified to the outlet stream because there is no chemical conversion. The particulate fraction of TKN is distributed in the same proportion as TSS. If the specified removal of TBOD5 is so large that the resulting effluent TBOD5 is smaller than the influent SBOD5, the model will adjust the percent removal so that the effluent TBOD5 is at least equal to the influent soluble BOD5 concentration. Now let's talk about the sludge thickening or sludge treatment. Gravity thickener is actually one of the first steps to increase solid concentration in the sludge. And here again, what we have to determine is the TSS capture efficiency and sludge concentration. So it's very similar to the primary settling. This reactor is modeled so that the user specifies the percentage of the solid capture and the expected sludge concentration, and the program calculates the sludge flow rate. Otherwise, the program calculates VSS, particulate BOD5, and particulate TKN, assuming that they are distributed in the same proportion as the TSS. Soluble BOD5 and ammonia are distributed in proportion to the flow rate. DAF, although the mechanisms is different from the gravity thickener, the calculation is pretty much same as the gravity thickener. So this reactor is also modeled so that these users can specify the percentage of the solid capture and the expected solid concentration. All remaining parts are identical. So just within the program, there's no actual difference between the gravity thickener and DAF. In reality, they are quite different. However, when you just wanted to calculate the removal efficiency, the principle are just identical. Again, solid dewatering can be done. One thing that we have to be careful is the values that we have to choose for this solid dewatering. So compared with the gravity thickening and dissolved air flotation, the solid capture efficiency and K concentration, especially the K concentration, is really high, because in here we are talking about more like a solid material rather than the slurry materials. If we apply this slurry dewatering, so we'll see very high concentration of dewatered solid concentration. Okay, the last part of the unit process in steady is this one, the mixing box and splitter box. So you can actually combine several flow streams into one, or you can actually separate from one stream to many other streams. And you can also choose the ratio among different streams. For instance, if you split that, you can actually set up the flow fractions. So in this case, the flow distribution flows are uniformly distributed. However, in reality, we may have more flows here, or a smaller portion of flow may be in other places. So that's all depending on the situation, but in this program, user can adjust that kind of parameters. So these are pretty much that you have to learn before you actually start using steady. So all details will be further. I'll also explain all other details when I actually show you how to use steady in the class. Thank you very much.